Hi again. I hope you're all enjoying the event so far. Welcome to How Open RAN Architectures Are Unlocking Technologies for High-Value Novel Use Cases. I am pleased to introduce Tim Rogers, the Director of Wireless Technology at Cambridge Consultants, and Rob Maunder, Founder and CTO at AccelerComm. Gentlemen, over to you.
Thank you very much, Catherine. I'm Tim Rogers. I'm going to talk about how Open RAN accelerates the development of high-value novel use cases. And these are business opportunities that go beyond the standards that are not met by solutions from the large network vendors. And while these may require considerable investment, they can unlock extreme value for enterprises and create a defensible moat of technology. So we've been working, if we look at some of the examples here, so we can see high altitude platform. And so this has real potential to provide coverage at a fraction of the carbon footprint of terrestrial or indeed satellite constellations. There's some real challenges in delivering this. So the platforms have an altitude of around 20 kilometers, and we're trying to light up maybe specific transport corridors or event stadium. And to do this, we clearly need very tight beam forming. In addition, these platforms are moving. So we need dynamic response on these beams as well. So we end up needing very large active antenna arrays to give this performance. And as we're on an aerial platform, the size of these and we're talking about 2 gigahertz here. So these arrays are measured in meters. The size and the weight, of course, of these arrays become a considerable challenge. And then also at these altitudes, the atmosphere is very thin, and so cooling is also a challenge. So we have very tight thermal constraints on the performance here. So Cambridge Consultants, we've addressed all of the use cases that you can see there over a number of years. Indeed, some of them sort of date back to before the O-RAN sort of paradigm was developed. And it's this sort of depth in the timeline that really, we've experienced the difference that Open RAN has made. So Cambridge Consultants, we deliver tough, high risk challenges, overcome them for world leading brands and for ambitious startups. We believe in a future that's unconstrained by current thinking, and we invest in deep technology to back that up. So technologies like quantum, like digital service innovation, artificial intelligence, and of course wireless systems. And so if we focus on wireless systems, we've got a full depth of skills from RF antenna phased array design through to digital signal processing, through to protocol stacks, from the test design and test facilities across to system simulations. And so we can design and architect full radio systems as well as designing, developing those most challenging components within the system. So the Open RAN ecosystem, before the ecosystem existed, we found ourselves having to develop a lot of the components in the radio systems from the ground up. So these sort of greenfield developments, we would be designing, implementing the layer 1 PCB circuits, antennas, architecting, designing protocols, and implementing protocol stacks. Simply because there was no alternative really. And as the Open RAN system, as the Open RAN ecosystem has grown, we've seen a number of vendors, independent vendors that we're able to work with, and we also see the open source community delivering a number of alternatives. And so we can, rather than developing from a greenfield, we can build these elements in. And while system integration may not be perfect, this is lowering the effort, the timescales required to deliver some of these novel solutions. So it's definitely providing acceleration. So I want to turn now to another example, and this is some of the research that we've been doing. So we're looking here to bring the user experience to the center of the autonomous networks of the future. So here we're talking about the applications, the X apps, the R apps that are running on the RIC, deep inside the network, typically the RAN, these currently operate on traditional quality of service features like latency or throughput. Of course, the user experience is perhaps what matters most to the end users, and this manifests at the application that's typically running on the mobile device. Now, we don't want to be modifying that application to be reporting user experience, nor in fact do we want to be using the valuable air interface bandwidth to deliver that. So we've developed an X app that runs on the RIC that predicts the user experience, infers it from layer 1 and layer 2 standard operating sort of parameters available on the E2 interface. So we've done this using open source. We've developed a training gym. It's the open air interface, open source, and we have upgraded the simulated radio interface, so we get a real full spread of performance. And using this, we can both generate training data and also run the system in real time and see that performance. So I'm just going to move forward now to consider a client project where we worked with AccelerComm. So AccelerComm deliver high performance, scalable, portable physical layer IP, and we use this to deploy on a 5G radio unit on the satellite. So I'm going to hand over to Rob now to explain the details there. Over to you, Rob.
Thank you, Tim. And it's a great pleasure to be here with you all today. I'll be talking about some work that we did in collaboration with Cambridge consultants on our product LeoFi, which is a 5G non-terrestrial network regenerative payload. And in particular, our focus here is the layer 1, the physical layer of this. I'll start by talking a bit about AccelerComm. So we are an IP company. We write code that runs in CPUs and in accelerators like FPGAs or ASICs. We license that code to our customers who integrate it onto their chips, onto their boards, into their boxes to build 5G equipment. And we make that easier for them by ourselves integrating the IP onto a development board, implementing all of the interfaces from the physical layer into the radio front end and into the layer 2 above. And then making that development board available to our customers to ease their integration. So our focus in this particular piece of work was a non-terrestrial network physical layer. And there are some key customer care abouts in the deployment of a 5G non-terrestrial network system. So first one here is quality of service. There were some quite particular challenges associated with satellite communication. So these include the high propagation distance from the ground to the satellite, which imposes significant path loss as well as delays, which are much greater than those encountered in terrestrial networks. There's also the Doppler effect as well as the satellites move quickly through the sky. Other aspects that are key care abouts here are the size, weight, and power. So satellites are constrained systems. They run on solar power. They have to be very tightly managed in terms of thermal dissipation. And so all of this points towards embedded computation. And then there are other constraints imposed on the computation platform, which is that the devices have to be space qualified. And then on top of this, there is a need for modular design based on standardized interfaces. The key to this is that there isn't a box that you can buy off the shelf and put on a satellite and be done. Every satellite deployment has particular requirements, particular needs, that can only be met by sourcing different components from different parts of the ecosystem. And so having standardized interfaces is important here for ensuring that all that can be integrated in a clean way. So I'll tell you a little bit about our LeoFi product here. So this comprises, as I mentioned before, software that runs on an embedded commoditized processor, like an ARM processor. So we have complete implementation of the 5G layer 1, and this is a highly configurable architecture, which is scalable to different types of CPU. And in concert with this, we also have high-performance hardware accelerators that run in an FPGA. And we have accelerators here for channel coding, like polar code and LDPC code, as well as equalizer and OFDM modulation and demodulation. So these are designed to give high performance with the combination of low power and small footprint. We have Open RAN interfaces between various different parts of the system. I'll elaborate on that in a slide in a moment. And this is an openly licensable solution, which maintains hardware platform independence. So the physical layer that we offer is a part of the non-terrestrial network GNO-B base station on a satellite. And in order to build the complete satellite payload, we have an ecosystem play where we work with partner companies who deliver the other parts of that system. So that includes lo-fi, the OFDM modulation and demodulation that I mentioned before, as well as the layer 2 and layer 3 aspects. We partner with other companies to deliver these. And in that ecosystem, we have demonstrated the integration of all of these parts via standardized interfaces. And what that gives us is a modular, space-qualified solution with support for SNL band applications, as well as a roadmap to KU and KA band deployments. What I'll talk about here is the different interfaces that we have between the various different parts of the system. Within the physical layer, which you can see on the slide here as a gray box, there are two parts. There's the software and there's the hardware accelerators that I mentioned before. And the interface between these is an AXI interface, but there are ORAN standardized interfaces here called the accelerator abstraction layer, which can be used here to standardize that interface there. There's also an interface between the Hi-Fi and layer 2 above. This is at the split 6. And for this, we used the NFAPI protocol from the Small Cell Forum, which is carried via an Ethernet cable. Between the Hi-Fi and our partners Lo-Fi, we have a eCPRI interface. This is based on the ORAN low-level split interface, and that's carried by an AXI streaming interface as well. And this represents the 7-2 split. And then from the Lo-Fi to the digital front end, there's a JESD interface, and this represents a split 8. So you can see there's a lot of different interfaces that build up the modular system, a lot of different splits, a lot of different standardization organizations involved in this. So to talk about the collaboration with Cambridge consultants, we approached them to help us fast track the development of this system, drawing upon their experience of previous developments, which Tim mentioned before. And there's a complementary skill set here, as well as the design services that Cambridge consultants offer. So the focus of the collaboration for the Cambridge consultants team was the extraction of a layer 1 feature set requirements. So this came from interrogating the commands that are issued by the NFAPI interface from the layer 2 into the layer 1 to catalog all of the different features that the particular partner's layer 2 was asking of the layer 1. And then the Cambridge team helped us by defining a set of functional tests to prove the correct operation of those requirements. The Cambridge team also implemented and simulated and validated particular software features. Examples of this were the sounding reference signal, part of the 5G uplink. Other aspects were the PRATCH signal as well. And then implementation of end-to-end tests and automation for these particular features that the Cambridge team had developed as well as other uplink channels. And together we built a test environment that comprises test equipment, signal generators, signal analyzers, as well as a stand-in for the layer 2, which can stimulate the layer 1, as well as the test equipment with commands to configure it into particular modes. And this test environment is fully automated, and it represents CI/CD. So whenever a line of code gets changed, the complete suite of tests can be rerun very quickly. So to summarize here, the deployment of a 5G non-terrestrial network system is it's an emerging opportunity which is going to have a big impact on the world in years to come. But there are a lot of challenges there. And these are challenges that AccelerComm has faced and overcome. And we're now in a very strong position to deliver these systems into diverse deployments that will be finding their way into space in the coming years. And this is through our LEO-Fi product, which has been tailored to deliver performance and reliability to meet the needs which I described before, the key care-abouts of a satellite operator. Thank you.
All right. Thank you both so much. We have time for a few questions. And actually, Tim, I'm going to start with you, and I'm going to try to combine some of the questions here and see if we can get a few people their answers. We have a few questions here that touch on the specific technical advancements or breakthroughs that have been achieved on the physical layer in order to address novel use cases or unique communication needs of tightly integrated verticals like mining and industrial automation. So maybe you can just discuss that a bit. You're muted, Tim. Tim, you're on mute, if you can hear me.
Yeah, sorry about that. Yeah, so yeah, we talked about some of the advancements in the antenna arrays, and clearly the physical layer also needs associated changes to match the sort of compute demands of those arrays. So for instance, if we consider the mining use case, I mean, there's a lot of challenges there around the determinism. The detonations, they need to happen. They need to happen in a fixed sequence, and so focused on the low latency and the ultra reliability there. There's a lot that's needed on that side, and a lot of additional sort of redundancy involved there. So additional transmit, receive points, etc. So, and then coordinating all of those can be quite some significant challenge.
Great, thank you. And Rob, I'll direct this next one to you. So this one says, in the context of autonomous network operation, can you elaborate on the technical aspects of how this capability is implemented and how it contributes to meeting the demanding communication requirements of specialized verticals like airborne or satellite systems?
Yeah, so there's some quite significant challenges here, particularly in the satellite systems. So in these ones, typically you have a beam hopping arrangement where the satellite is casting different beams onto the surface of the Earth to give coverage to different geographical regions. But quite typically, not all of those beams are activated at every moment in time. Only a subset of those are used. And over time, on a very fast basis, the different beams are being hopped on and off. And so this imposes some particular challenges for the deployment of a 5G NTN system because the terrestrial networks don't quite have that same concept. And so the beam hopping imposes particular constraints within which the rest of the network optimization must work. And so what this implies in terms of O-RAN standardization is new interfaces to allow that coordination for the beam hopping management to impose constraints upon the layer 2 scheduler, and for the layer 2 scheduler to let the beam hopping management know that there are users who are demanding service. And so that could be a RIC implementation, for example, or there could be other ways of doing this.
Okay, and that puts us at time. So thank you, Rob and Tim, again, and thank you to our audience for listening in. Up next, we have an interview with the DISH executive that questions if the RIC is the make or break solution for Open RAN.